Hello, we're going to talk about quantization of rotational energy. So I'm going to share my notes. Okay. Okay. So we talked about quantum mechanics in general and the postulates behind it. So the structure that led to quantum mechanics. And then we went carefully through translational motion. So particle flying through space, um, and looked at the fact that that's quantized if there are boundary conditions. And so now we'll talk about rotation and then we'll talk about vibration. So these are all different places you could put energy in a molecule. So we'll discover in this topic that the energy and the angular momentum of a rotating object are quantized. And so there's a little section on angular momentum. I'm going to go through it because I feel like it's probably something that's not a review, but something new to you. So angular momentum, based on the idea of angular velocity, which is usually given the Greek letter omega. So there are 2 pi radians per 1 cycle around a circle. And so omega is usually given in units of 1/seconds or 1/time. And that's implied that it's a radian per second, so that you're moving a certain number of radians. But the radian is just usually left off and implied. So we're going to think about angular momentum in a similar way that we think about linear momentum. So linear momentum, which is given the symbol P, is the mass of a particle times the velocity at which it's moving. And so the angular momentum has a similar definition. Angular momentum J is equal to I, the moment of inertia, times the angular velocity. So I is the mass times the radius at which something is traveling in a circle, so squared. So I equals mass times radius squared. So if you just have a 2 dimensional rotation, so for example, this diagram is meant to show you that you have the z-axis and there's a particle rotating at some radius with some mass around that axis. Then you would say the angular momentum around the z-axis, so jz, is equal to the moment of inertia around the z-axis times omega around the z-axis. So angular momentum equals I times omega. And if you're talking about that motion around a particular axis, then you would look at J. You could also have, or JZ. You could also have JX and JY if it's a 3-dimensional particle, if it can move in all dimensions. But we'll look at separating that into 2 dimensions and 3. So, angular momentum has the units of distance per second times r times m. And oh, yeah, so we'll see where the other r comes from here in a second and how we get I separated out from that. So angular velocity is radians per second. The moment of inertia is mass times r squared. And so radians times r equal distance. So if you go back up here, one of the r's times radians is going to equal the distance. And if you're talking about the angular velocity, so then that's the distance per second. And then you're still left with an r and an m. And so when you look at that, that's going to be equal to momentum times r. So that's going to be equal to mass. The velocity is the distance per second, and the distance per second is radians times r per second. So if you separate that all out, you get momentum, and you're left with 1r. So the angular momentum is I omega, and that's equal to linear momentum times r. So kinetic energy we already defined when we talked about our translational particle, and that's 1/2 mv squared, so 1/2 mass times the linear velocity squared. And if you want to do that in terms of angular velocity, it's also going to be equal to 1/2 I omega squared. So take a second to prove to yourself that this 1/2 I omega squared is equal to angular momentum squared over 2I, and then come back and continue watching. So first we'll talk about rotation in just 2 dimensions. So just like the picture up here, you have a plane and there's a particle at a fixed radius traveling around some axes. And so we'll call that axis Z. So moment of inertia is going to be the mass of that particle times the radius at which it's rotating squared. And so the angular momentum, and I put absolute value because it can be going in 2 different directions, and we'll call one of those positive and one of those negatives. But that's going to be equal to momentum times R, which is what we showed up here. JZ, the angular momentum around a fixed axis, is equal to IZ omega Z. And we showed that that equals linear momentum times R. And so now we want to think about, how do you think about the fact that it has to be quantized? What's its boundary condition? In the particle in the box, we had the boundary condition that the wave function had to meet the walls and be at the same value. Here we'll see that when you go around a circle, you have to have a boundary condition. So we could solve this exactly with Schrödinger's equation, look at the wave functions. Instead, we're going to do a more qualitative solution and just look at the energies and not the wave functions themselves. If you take an upper level Chem 367, we'll solve this using Schrödinger's equation and have more information. But all we want to know is it quantized? Does the energy only have allowed values when you put it into exciting the rotational motion in a molecule? So if we go back to where we started with quantum mechanics, de Broglie postulated that the wave length of a particle is equal to Planck's constant over momentum. Therefore, momentum equals Planck's constant over wavelength. So if you plug that into our equation for the angular momentum around the z-axis, first we know that energy is all kinetic, and so it's momentum squared over 2m, just like it was when we looked at the particle in a box. But now we know that angular momentum squared would be equal to p squared r squared. And so we can put our definition of momentum in terms of angular momentum in. And we end up that the energy is equal to angular momentum squared over 2I. So you can convince yourself of that. And now if we put in the definition of momentum, so let's see. Yeah. If you go back here and put in your definition of momentum in terms of wavelength, what you find is when we take this equation in black and put in the fact that momentum equals h over lambda, we end up with this equation, hr over lambda, instead of momentum squared over 2m. And so when we think about what solutions are possible, so the wavelength has to be equal to the same thing once you go once around the circle. So if you go around the circle once and return to the same location, that angle plus 2 pi, the wave function has to return to the same value. If it doesn't, then you're going to have more than one value for the wave function as it goes around the circle again. And so we're limited to wavelengths where n times a wavelength. So you have an integer number of wavelengths in the circle. So the circumference of the circle is 2 pi r. And so we know that we have to have an integer number of wavelengths fitting around that circumference. Otherwise, we won't return to the same value. So n can have the value of 0, 1, or 2, or up to infinity. And so if you just rearrange this equation in purple, that means that the wavelength has to be 2 pi over r. And if we look at angular momentum is equal to momentum r, yeah, and then put in for momentum h over lambda. So h over lambda is momentum. Momentum times r is equal to the angular momentum around the z-axis. And so now we know that the wavelength can be replaced with 2 pi over r. So if you do that and rearrange it, you see that the angular momentum can only have certain values. N, an integer value, times h divided by 2 pi are the only possibilities. That can be plus or minus. So we're going to replace our quantum number n with m sub l and give it a different range of quantum numbers. So it can be 0, but then it can be plus or minus 1, plus or minus any of the integers, just meaning that it's either going clockwise or counterclockwise. Each of those would have the same angular momentum value, but it would have a different sign. So angular momentum has to be quantized if we're going to get a wave function that's single valued. That was our boundary condition. And so the angular momentum is going to be m sub l times h bar. So I got rid of the absolute value because now our m sub l has the sign. And the m sub l value can be 0, plus or minus 1, plus or minus 2. So angular momentum is quantized. So that also implies that energy is quantized. So if energy equals angular momentum squared over 2I, which where did we introduce that? Right here. So angular momentum squared over 2 times I. Remember, mr squared in black, that's I. So if energy is a function of angular momentum, therefore it's also quantized. Its energy is a function of m sub l squared. So it doesn't matter if it's going counter or clockwise, it will have the same energy. So you'll have degenerate energy states. And then h bar, remember, is h over 2 pi, and then 2 times I in the denominator. So angular momentum being quantized implies that energy also has to be quantized, because energy, when it's all kinetic in rotational motion, is a function of angular momentum. So some of the things you notice about that is that you have degenerate states going clockwise and counterclockwise have the same energy, but they're different states. Energy is independent of direction, which makes sense. If m sub l equals 0, it's non-degenerate, and there's no 0-point energy. So if m sub l is 0, then we look at our energy equation. That means energy 0, and there's no rotational motion. So there's no 0-point energy like there was with translational motion. So stop and work self-test 7D.1. And now we'll talk about rotation in 3 dimensions. So this will be a good model for our solutions for electrons moving around a nucleus. So our next chapter is going to be focused on the hydrogen atom, where you have the proton in the middle, and you have an electron that can move on in all directions. So it's not just 2-dimensional. So let's look at the coordinate system. I'm going to stop sharing and pull up the coordinate system. Okay, so go back. Here it is. So now we're going to also work in spherical polar coordinates, because that's going to make the most sense for solving our problem. We tried to work in Cartesian coordinates. We wouldn't be able to separate the coordinates from each other, and we wouldn't be able to do the solutions. So we have a distance from the nucleus out to the surface of the sphere. Then we have theta, and we have phi. So we have phi is the angle around the z-axis, and then theta is the angle with the z-axis. So that's the coordinate system that we are going to use, because that will allow us to solve this problem. Go back to my notes. So our wave function is going to be a function of theta and phi. So we're not allowing the particle to move closer or further away from the nucleus, if we're talking about an electron around a nucleus in an atom. And we'll see that we can solve that motion separable. So we can separate the theta solution from the phi. So like motion of a particle in a ring, but now the particle can migrate from ring to ring. And so we're going to have two different boundary conditions. And we'll call the quantum numbers for those two boundary conditions m sub L and L. So both theta and phi, when the particle rotates through 2 pi, have to return to the same value for the wave function. Therefore, we have two boundary conditions, and that gives us two quantum numbers. First quantum number L can have values 0, 1, and 2 up to infinity. M sub L depends on L, can go from 0 plus or minus, all the way up to plus or minus L. And we'll see that the quantized energy values are a function of only L. So energy equals the quantum number L times L plus 1 times h bar squared over 2m r squared. So remember, L can be 0, 1, 2, integer values including 0. So these wave functions are called the spherical harmonics. So we're not going to look at them right now, but we're going to look at them when we look at how we use them for the hydrogen atom. So there's solutions that are a function of both theta and phi. And let's see. Because the energy is quantized, we know the angular momentum is quantized. So when we're looking at the functions, we won't look at those in this focus. We'll look at them in topic 8. But when we look at the energies, just like with two-dimensional rotation, if energy is quantized, then so is angular momentum. So if you look at the relationship, the angular momentum has to be L times L plus 1 to the 1/2 times h bar. And figures 7 and 8. I'm going to stop and look at those. I can't remember if I wanted to look at them before or after you talked about, looked at the vectors. Let's see. Yeah, I think you want to read the chemist toolkit first on vectors. I'm sure you have a pretty good memory of vectors, and then we'll go through these slides. So I'm going to go back to my notes, and then I'll come back to these. I wish it would just let me do that without stopping and starting sharing. So read the toolkit on vectors. Angular momentum is a vector, meaning that it has a value and it has a direction. So if we talk about angular momentum about the z-axis, then that's the component that's of the vector that's rotating about the z-axis, but it could also be rotating about the x and the y-axis. So angular momentum equals jx, jy, and jz. So it's the sum of all the angular momentum. And let's, before you do self-test 9 or D2, let's look at the pictures and how we have to represent. I think this is the very best one. So there's a lot to talk about in this. So if we have an angular momentum of 3, so this is figure 9, there are 7 different orientations. So it can have 7 different m sub L values. M sub L is the orientation or the projection of the angular momentum onto the z-axis. So if you were to represent it just with a vector, it implies that you know jz, jx, and jy, but you can't know all of those because if you did, you'd know the position and the momentum and you'd be violating Heisenberg's uncertainty principle. So this just shows you that the projection onto the z-axis, so the z-axis is given with the -3, -2. So that's the m sub L value for the projection on the z-axis. It could even be 0. But it's better to represent these not as vectors with known x, y, and z components, but as cones. So in this red cone, you see that we know the projection onto the z-axis, but by representing that as a cone, we don't know the projection onto the x or y-axis, so we're not violating Heisenberg's uncertainty principle. Same thing for the orange. The projection on the z-axis has an m sub l of +2, but we don't know the projection on the x and the y-axis. So angular momentum has 3 components if it's 3-dimensional, and we can know the projection onto one axis, but not all 3, because if we knew it on all 3, we'd know the position and the position and the momentum in all dimensions, and that's a violation of Heisenberg's uncertainty principle. So I'm pretty sure I just want you to do that one self-test. Yeah, do the last self-test 7D.2, and then come back and I'll have another lecture where we'll go through vibrational motion.